Hello everyone, this is Connor with the Aerospace Engineering Fellows, bringing you a video in preparation for Exam 1 of ASEN 3111 Aerodynamics. We're going to be covering some Calc 3 concepts, so let's get into it. So first I want to talk about this del operator, right? Sometimes it's called grad, I call it del. And del is kind of like a vector, but it's more like a vector function or a vector operator because the things it applies to, it doesn't really get multiplied by, stuff like that. It operates on them, it differentiates them, right? So this is kind of the vector form it takes, right? And when we use it in math, we take the partials of whatever ends up in the component with it, right? So with that, we'll move on to gradients, right? So a gradient is kind of like, I got a nice little picture. It's kind of like the contour map of a scalar field. So if you have some density field, some scalar field, you can even think of it as like altitude as a scalar field, right? At every x, y, and z point, or every x, y point, there is some h associated with it, right? And you can quantify the steepness or the slope of some mountain if you would take the gradient of that altitude field, right? And so how we carry that out is we take the partial with respect to each dimension in our field, right? So if we're looking at a three-dimensional field like pressure, this pressure field P, we're looking at how it changes in each direction, right? It's kind of like the slope in the x direction. So x slope, y slope, and z slope. This tells us how steep it is in every direction, right? If we look at this in the same way for a vector field, we'll say that we'll pose the same thing again, the contour map of a vector field. And that actually doesn't make a lot of sense, right? If you have a bunch of velocities, how do you quantify the highest velocity? Is that the highest magnitude of velocity? Is the velocity with the highest individual component? It doesn't make a lot of sense, right? This is actually not a real quantity. It's not something that exists mathematically. Another way you can think about it is we're kind of multiplying two vector quantities, and you don't multiply vector quantities by just sticking them next to each other, right? If you're going to multiply them, you're going to do a cross product or a dot product, right? So that's one way you can remember that the gradient of a vector field does not exist. Moving on to the divergence of a vector field, right? So the divergence of a vector field, and we'll talk about it in the context of velocity, and specifically we'll use some lingo that's specific to velocity fields. So divergence of velocity, right, is the time rate of change, rate of change of the volume of a moving fluid element per unit volume. And a moving fluid element has fixed mass. That is the one little thing that I left out trying to go off memory there. Right, so divergence of velocity is called the dilation. And it basically tells us, is this flow moving away from itself or moving toward itself? Is the volume with respect to volume, per unit volume, changing? So like if you have some fluid element, some material element with constant mass, is it getting bigger, right? And if it is, that implies that our density is changing, right? And if that's the case, this is a compressible flow, right? So if we have this dilation not equal to 0, we're seeing compressibility, right? And that applies in some of our assumptions we make as we develop different tools to analyze flow, and you can remember that and keep that in your toolbox on your crib sheet, right? But essentially this is what this means in terms of specifically a velocity field, and in any vector field, basically, is it moving away or towards itself, right? This is the actual equation for it. It's just the partial with respect to Vx, partial of the x component of the field with respect to x, y component of the field with respect to y, z component with respect to z, all summed up. And that's basically what, this is a very literal dot product between this del and v operator, right? So we have the partial x, partial y, partial z, and then Vx, Vy, Vz, right? So if we kind of operate on like components and then we add them up, that's just what a dot product is, right? And if we take that logic and we move on and we say, what's the divergence of a scalar field? What's a dot product with a scalar? What? That doesn't make any sense. This is another one of those where it's not a mathematical thing. You wouldn't take the divergence of a scalar field because the scalar field doesn't have any direction associated with it, right? We can make direction if we make a gradient. We can say, oh, it's steeper in this direction, or, you know, but that involves taking the gradient of a scalar field, right? So you can't outright take the divergence of a scalar field, right? So, moving on. Now we talk about the curl. So the curl of a vector field, how twisty is it? And you can see I've already drawn arrows on here, right? So this kind of implies that we have some flow, some vector field that's like moving around, and it's got you know, these velocity components, and we can quantify how much it's twisting. And in the same way that you kind of quantify, you know, we have these, you know, these linear or these straight lines, and we want to quantify kind of the rotation about, you know, the rotation that these lines imply, right? So we usually do that with a cross product, right? If we're going between rectangular to curvilinear, or I don't think those are the words I'm looking for. If we're going between linear and rotational motion, right? If you wanted the linear momentum, it's just, you know, mass times velocity. If you wanted the angular momentum, it's the mass times the angular velocity, right? Where the angular velocity is r cross v, right? Maybe it's backwards. No, it's r cross v, definitely, right? Same thing over here, and we'll just talk about this in terms of a 2D flow, right? Where we only have a z component for this cross product, and this is what we end up with. And here I've defined v equal to u, v, and w. Generally, pretty standard for what you'll see in a general aerodynamics problem, right? Taking this a step further, just like we did with the other ones, what does it mean to take a cross product with a scalar? That's bogus. That's wrong. You can't do that. That's not a thing. That's not a real mathematical thing, right? And so that's what I have for you. This is the curl, divergence, and gradient of different fields, right? And I've listed out some of the equations in Cartesian coordinates. If you want to find out these cylindrical and spherical equivalent equations, I encourage you to check out Anderson. This is the 6th edition I'm using, but equations 2.16 to 2.22 have all those equations and all the coordinate systems that'll be useful for you. Very helpful on a crib sheet, I would say. And I think with that, I'll sign off for this video. Thanks for watching. If you have anything you want to bring up with us, you know our email. It's in the description. And have a good night.